We're now going to learn about molecular orbital theory. And this gets developed because the Vesper theory and hybridization or valence bond theory are really good at, they build on each other, they deal with shape, they deal with the orbitals, and how atomic orbitals convert and make other shapes. But they don't explain certain magnetic and spectral properties. So, for example, O2, oxygen, if you look at it, it looks like all of the electrons are paired and it should be not magnetic, or what we call diamagnetic. But in reality, it actually is. Liquid oxygen does have magnetic properties. And it also doesn't talk or discuss much about the spectral properties such as infrared or UV properties. So molecular orbital theory does address these shortcomings from these other theories. And it has, basically, we're going to be dealing with two atoms at a time bonded together. And so it is going to have a lot of characteristics that are similar to atomic orbitals that we've dealt with. So 2 electrons go in per orbital. The spins have to be opposite. There is a definite energy of orbitals, right? So low energy fills first. And it also is a wave function based, so similar, right? It has s and p orbitals and those kinds of things. But they differ because we're dealing with the entire molecule, or in this case, in the case that you'll deal with, is between 2 atoms. So like A bonded to A, so like A2. That's not a real molecule, but like O2 or Cl2, or even like HCl, right? So 2 things, they don't have to be the same atom. But when we have 2 atomic orbitals that overlap, we're going to have 2 molecular orbitals that get formed. So far we've just said, like, from the valence orbital theory, we said, like, okay, I have an s orbital here, an s orbital here, they overlap, cool. We get a bond. But what we get with MO theory is that we get one bonding orbital that comes out and also one anti-bonding orbital. So what do I mean by anti-bonding orbitals? So basically what happens that we say is that we take these 2 orbitals and we put them together. And when we bond, we have constructive combination. So we're adding. So this is when we add the orbitals together. But we also get anti-bonding orbitals, which is the destructive combination where we're basically subtracting these two orbitals together. And what you get when that happens is a nodal plane or a break where no bond can form. We denote the bonding orbitals with a sigma, just like we have with it is a sigma bond, and anti-bonding with a sigma star. So when we have the formation of H2 molecule from these 2 hydrogen orbitals, they come together, they're each 1s. We have the 1s come together and form a covalent bond. And then we have the anti-bonding orbitals show up here. But there's a little bit more to it that we'll get to next. Now what we do is we draw an energy level diagram, just like we had an orbital diagram before, right, where we had like 1s and we did like 2 and like 2s, 2 like that. But now we're going to combine atoms together. So what you'll do with these is you'll take your atomic orbitals to each side, so 1 atom on the left, 1 on the right. You put the valence electrons in there, and then we draw the bonding orbital or sigma orbital below and anti-bonding orbital above. So high energy, again, meaning unstable or repulsive. Low energy, meaning stable or attractive. So just like before, we're going to, we wrote a number of electrons that go in each orbital. We're going to then fill the lowest energy first. So we have 1 electron from this atom, 1 electron from the other atom. So we fill in the 2 electrons in the bonding orbital. So when we do that, we can see that 1 sigma bond is produced. So how stable the bond is related to something called the bond order. Bond order is a calculation where you take half the number of bonding electrons, subtract the number of anti-bonding electrons. So in this case that we did above, up here, we're going to do 1/2. So the order is 1/2 times 2 electrons in the bonding orbital down here and minus 0 electrons above. So our bond order is 1. And this basically corresponds to it having a single bond, which is what we see with hydrogen. It has a single covalent bond. You can also do electron configurations for your molecules now. So we can see here we have our sigma bond, or a sigma orbital in the 1s, and there's 2 electrons in it, and then we don't have any in the antibonding. So for the H2 molecule, I would write my electron configuration as sigma 1s with 2 electrons in it, and that's it. Let's see, moving forward, you'll see it can get a little bit more interesting. So now we're going to ask the question, can He2, can helium molecule form? We're going to use molecular orbital theory to decide. So what we'll do is we'll say, okay, each helium atom has the valence electrons are in the 1s orbital, so I'll do 2 of them over here. And then we're going to draw it, the energy, and I'm going to draw those electrons in here, 1s2 orbitals. And then we're going to draw the sigma antibonding up here and the sigma bonding orbital right there. So we have 4 total electrons here. So we'll fill it in, starting with the lowest energy, 1, 2, and then 3, 4. So here we have for this molecule, we have both the bonding and anti-bonding molecular orbitals are occupied. And so let's calculate the bond order. And we'll do 1/2 of the number of electrons that are in the bonding orbital, so 2, minus the number that are in the anti-bonding, 2. So 2 minus 2 is 0. So this means that there is no bond here. There's no total bond. The bond gets canceled out with the anti-bond, and so He2 does not exist. Then, as we want to do our electron configuration for this one, we will take our sigma in our 1s and say there are 2 electrons in there. And then we'll do our sigma antibonding up here for the 1s orbitals, and it also has 2. So this would be the electron configuration of helium, the helium molecule.